Somewhere far beyond everything familiar, in total darkness and cold, where temperatures fall close to absolute zero, two tiny objects are moving through space. Each one is about the size of a small car. They are so far from Earth that a radio signal from them takes more than 22 hours to reach us. Nothing humanity has ever built has gone farther. And here's the unsettling part. They are dying. Slowly, quietly, inevitably. Their nuclear power sources are fading. Engineers at NASA carefully shut down one instrument after another, trying to buy a few more months of life. Maybe a year, maybe two. And then, one day soon, the signals will stop. Forever. But in nearly 50 years of flight, these two machines have already changed how we understand our place in the universe. Their story begins in the late 1970s, in a very different world. The Cold War was still raging. The Apollo program was over. Space exploration seemed to be losing momentum. That's when a small group of NASA scientists realized something extraordinary. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, were aligning in a way that happens only once every 176 years. With the right trajectory, a spacecraft could visit all of them, stealing a bit of gravity from each planet like a cosmic slingshot. Miss this opportunity, and the next one wouldn't come until the 22nd century. So NASA took the risk. In the summer of 1977, two Titan Centaur rockets roared into the sky from Cape Canaveral. At their tips sat two nearly identical spacecraft, Voyager 1 and Voyager 2. They were designed for a 5-year mission. 5 years. No one imagined they were launching the longest-running space mission in human history. The engineers were cautious, almost paranoid. Redundant systems, backup engines, duplicate instruments, and most importantly, radioisotope power generators fueled by plutonium-238. No solar panels, just steady nuclear heat converted into electricity meant to last decades. And it worked. Voyager revealed active volcanoes on Jupiter's moon, Io, the first ever seen beyond Earth. It transformed our understanding of Saturn's rings. It showed us Uranus spinning on its side, and Neptune with winds screaming at over 2,000 kilometers per hour, the fastest in the solar system. In just a few years, the original mission was complete. But instead of shutting the spacecraft down, NASA did something bold. They kept going. Voyager was sent toward the very edge of the sun's influence, into territory no human-made object had ever reached. Before that journey truly began, Voyager 1 was given one final command for its cameras. Turn around. From nearly 6 billion kilometers away, it photographed Earth. In the image, our planet is less than a pixel, caught in a random shaft of sunlight. A pale blue dot in a vast cosmic darkness. Carl Sagan later wrote words that still give chills. That's here, that's home, that's us. After that, the cameras were shut off forever to save power. What lay ahead was the unknown. The solar system isn't just planets orbiting a star. It's a massive bubble carved into space by the solar wind, a stream of charged particles blowing outward from the sun. This bubble, called the heliosphere, shields us from much of interstellar space. To leave it, Voyager had to cross regions scientists had only theorized about. The termination shock, the heliosheath, and finally the heliopause, the true boundary between our sun and the galaxy beyond. And when Voyager reached it, reality refused to follow the models. Instead of a smooth boundary, the spacecraft detected chaos, enormous magnetic bubbles, some as large as Earth itself, swirling like foam. The edge of the solar system wasn't a wall, it was turbulence. In 2012, Voyager 1 crossed the heliopause. Plasma density jumped dramatically, cosmic rays surged. Everything said, this is interstellar space. But one thing didn't change: the magnetic field. According to theory, it should have shifted direction. It didn't. Not at all. NASA scientists argued for nearly a year before finally confirming the truth in 2013. Humanity had left the heliosphere, but our understanding of interstellar space was incomplete. In 2018, Voyager 2 crossed the same boundary. Same result. Same mystery. Even more confusing, both spacecraft crossed at nearly the same distance from the Sun, despite very different levels of solar activity. Another prediction shattered. Today, both Voyagers are slowly fading. Instruments are freezing. Power levels drop every year. Engineers make painful choices about what to turn off next. Eventually, the transmitters will fall silent. And then, nothing. But the spacecraft themselves will continue. Voyager 1 will pass near a distant star in about 40,000 years. Voyager 2 will drift near Ross 248, then hundreds of thousands of years from now pass within a few light years of Sirius. Earth may not exist by then, yet each Voyager carries something extraordinary, a golden record, a message from humanity to the universe, music from Bach to Chuck Berry, sounds of wind, thunder, laughter, and heartbeats, greetings in dozens of languages, images of life, science, and our fragile world. The odds of anyone ever finding it are microscopic, but that was never the point. The Voyager mission is proof that a small species on a small planet dared to think in cosmic time, that we chose curiosity over fear, hope over certainty. Long after the last signal fades, long after Earth itself may be gone, those two tiny machines will still be out there, silent, frozen, drifting between the stars, carrying proof that once, on a pale blue dot, there was a civilization that looked up and tried to reach the universe. And maybe that's enough.